Alright friends, welcome back. In this video I'd like to go ahead and start chapter 1 by taking a quick look at section 1.1 from your textbook, and it's going to start to talk about equations and graphs of equations. So what I want to do is in this video specifically show you a couple of key tricks that you can be using with your calculator to kind of help you do various things from getting points to plot to getting a sense of the symmetry of graphs here. So let's get started with that. So graphing equations. Basically, in this first example, we are given this equation, y is equal to the square root of x plus 4, and the question is simple. We just are given two coordinate points, and our question is, are these points that actually lie on this graph, or are they not? Okay? And so, just going to the calculator really quickly, what we might do is pull it up. Here it is right here. When you first turn it on, you might be staring at this blank calculation screen right here. In order to get to the point where you can graph something, I want you to go ahead and click this button up top that says y equals. It's in the top left-hand corner. This is going to be your graphing space. And so for us, our function formula was the square root of x plus 4. I'm just going to go ahead and simply type that in and press enter. Just make sure really quickly that that is something that matches what's on your paper. It's always good to make sure that you typed it in correctly. And then once you type it in, you're just going to simply press graph. And it's going to create this nice picture of the graph here for you. And then one of the things that we're able to do, since I have a nice grid going on here in the background of my graph, is we could just go ahead and count out the coordinates and see if they lie on this this path or not. But one of the better things we might be able to do is go ahead and click this. Do second button and then graph. And what that does is it brings up a whole table of values, and in there you can definitely see that if I have an x coordinate of 0, that corresponds to a y coordinate of 2. And so that just confirms that, yes, that is a point that lies on this function, or this graph. If I have an input of 5, then that corresponds to an output of 3. Okay, so these are confirmations that you can be doing in the calculator to just check and see if you have these types of points on your graph. Now, that's a little bit more of a use the calculator to do it, maybe something that you could use to check your answer, but if this was a test or a quiz situation, we would want to be able to show the work for this. And the way that you would do that is just by remembering that each one of these points has an x coordinate and a y coordinate, and when you write out the equation, what you're doing is you are relating the y coordinate to its x coordinate. So all we're going to have to do is simply just plug in 0 and 2 in for x and y respectively and see if we get the same number on both sides of the equation. So if I plug in 2 for y and 0 for x, my question is, does this end up being the same number on both sides of the equal sign? Well, I think you'll find that it does, because whenever we do 0 plus 4, this is going to end up being 4. And the square root of 4, of course, is simply just a 2. And we end up with the same number on both sides, so that means, yes, this point is going to lie on that function because its coordinates work when I plug them into the equation. My goodness, that was a very intense answer box there, so let me go ahead and change that to something more like that. There we go. Okay. Same thing on this next example. If I have a y coordinate of 3 and an x coordinate of 5, I'm going to test to see if I plug them in, does this give me the same number on both sides? And I think you'll find that it does, because 5 plus 4 is 9, and the square root of 9, of course, is simply just 3. And so the answer for this one, of course, would be yes as well. So if you're ever asked a question about, is a point on a certain graph or not, then all you have to do is plug in the coordinates of those points and see if they give you the same number on both sides of the equal sign. Okay? Now, to graph an equation by hand, what we would need to do is create ourselves a nice table of values and then plug them into our equation and see what the corresponding outputs would be. But again, because we have calculators, this is actually a really, really easy problem to do. Because here in example 2, it says complete the table and then sketch the graph, which we'll go ahead and do up here on this grid right up here really nicely. Okay. If we are trying to do that, then again, all I'm going to do is I'm going to take the calculator and I'm going to go ahead and simply plug in my function formula. Y is equal to x squared plus 1. Okay, so let's go ahead and do that real fast. So let me go ahead and pull up my calculator here real quick. I'm going to go back to y equals, and my recommendation for you guys is that anytime you do a new problem, go ahead and clear the old one out and start fresh on y1. You don't really want to have two different graphs in the same viewing window. That's just going to lead to some confusion later on. Okay, so our function formula was x squared plus 1. I'm just going to type that in. I can press graph to get a quick sense of what that shape would look like, but what I'm really interested in is that table. So if I press second graph, then that's going to create for me this nice table of values here, and because the values that we want to go ahead and fill our table with here are just simply going to be the values that go from -2 all the way to +2, we can look at the table in our calculator for those values. Okay, so if I do those here really quickly, that's going to simply be 5, and then 2, and 1, and 2, and 5, and I could do it in a matter of seconds and not have to take each one and meticulously plug them into the function. Okay, and now that I have these, I can remember that, again, these correspond to ordered pairs that I can plot. So -1, 2, 0, 1, 1, 2, and then finally 2, 5. And I could plot all 5 of these points, get a nice skeleton for what this curve would look like, and then just go ahead and approximate the rest with a nice smooth curve here. So I'm just going to do that here really quickly. So 1 is going to correspond to 2. -1 is going to also correspond to 2, I believe. Yep. And then 2 is going to correspond to 5. And -2 also is going to correspond to 5. And so I get this nice little shape here, and I'm just going to go ahead and approximate the rest here by drawing a nice smooth curve through both of these. Okay, matter of fact, I think I plotted that one wrong, so let me try that one again. So I think I plotted the vertex of that incorrectly, so let's try that one more time. So I think I should be here, there we go. And then we'll plot these points and these. There we go, that looks a lot better. Doesn't look so narrow or vertically stretched. There we are. Okay, so again, rely on that calculator. And just as a short aside, if you ever had a set of directions that asks you about solution points, that's exactly what we just came up with here, are 5 solution points to that equation. Again, these are just points whose coordinates give you the same number on both sides of the equation after you plug them in. All right, really quickly, I want to talk about the intercepts of a graph here really quickly. So we have x-intercepts and we have y-intercepts. These are something that we've talked about before in the context of just simply equations, but now that we're in function territory, we want to kind of reiterate what these are in terms of functions. And so these are going to be points on the graph that have coordinates that correspond to some x value as its x-coordinate, but then 0 specifically as its y-coordinate. It works similarly for the y-intercept, where playing the role of its x-coordinate is 0, and then playing the role of the y would just be some number, right? So if I have an equation that looks like this, y is equal to x cubed plus 1, we can go back to the calculator, go back to y equals, and we could go ahead and plug that in here. So x to the power of 3, and then plus 1, press enter to lock that in, graph, so we can get a quick sense of what that shape would look like, and then we can go right to the table here, okay? So what I'd want to do here is pick out some x and y pairs that are going to fit nicely into the grid. And so if I start my list here at, let's see, -2 I think would work here for us. That is going to fit pretty nicely into our grid. -2, -7, -1, 0, 0, 1, 1, 2, and then 2, 9. I think these would be great points to go ahead and include on my my function. Okay, so let's go back to the graph and actually do that here, right? So again, I'm just getting these values straight from the calculator. So we had -1, 0, we had 0, 1. I believe we had -2. What did it say? I think it was 9, -9, and then just the rest in the following ways here. Okay, so now that we have that going on, we can go ahead and approximate the rest here with a nice smooth curve, and very quickly finish up a problem like this. Now, we want to identify the x-intercept and the y-intercept of what we've got going on here. So remember that the x-intercept is the point that has a 0 as its y-coordinate. Well, we just actually took a look at that, because the point with a 0 as its y-coordinate is going to be this point right here. It's going to be the place where we cross the x-axis. Okay, and so for us, that's going to be the point with coordinates -1, 0. Okay, that's going to be our x-intercept. Now for our y-intercept, we of course want to go ahead and take a look at the point that has a x-coordinate of 0, and that of course would be this point on our graph right here. Okay, so that would be the point with coordinates 0, +1. Okay, so after we get that table of values from the calculator and plot the points and create a nice sketch of the graph, it's very easy to take a look at where your graph crosses the x-axis, where it crosses the y-axis, and point those out as the x-intercept and the y-intercept respectively. Last thing I want to talk about in this video is this concept of symmetry. So this would be folding symmetry. So can I fold along the x-axis and overlap on top of itself? Can I fold along the y-axis and overlay on top of itself? Or in the case of origin symmetry, what we're talking about there is more of a rotational symmetry. Can I rotate the shape of my graph around the origin and then get the same exact shape overlapping on top of itself here, okay? Well, visually speaking, that would be something that we can kind of check the calculator for, but we would like to go ahead and have an algebraic way of doing this, because that's more objective and proves our result in a little bit more of a algebraic way here. So in order to do that, we would have these tests for symmetry, and the tests work in the following way. We would simply just go ahead and replace each y we see with negative y, and then see if we result in the exact same equation as before. Works the same way with y-axis symmetry, where we would replace all of the x's we see with negative x in parentheses, and then simplify and see if we end up with the exact same equation as we started with. So in the cases of those two tests, it would just basically be said as, can you plug in negative y and nothing changes, or can you plug in negative x and nothing changes? In the case of origin symmetry, what we would want to try to see if we can do is plug in both. Replace y with negative y in parentheses, replace x with negative x in parentheses, and see if we would get any changes associated with those. If we don't have any changes at all, then that means that we will have that type of symmetry. Okay, so I just want to go ahead and demonstrate that with this first example here. So we have this equation, x is equal to y squared minus 3. What we want to do is first test for x-axis symmetry. And so what that's going to mean is I'm going to take all the y's that I see, and I'm going to replace them with negative y in parentheses, and then simplify. Okay, so my original equation, nothing else is going to change except that y is going to change to a negative y. And I'm going to write out all my other operations in my equation here. Now, what I want you to notice is that y was being squared in this equation initially, which means that if I take y out and I replace it with negative y, now negative y is being squared. And we all remember that if you square a negative number, that just ends up being positive. So by squaring that y, or sorry, I should say by squaring that negative y, I get my original equation back again. And again, that's what you're looking for in order to check to see if you pass the test, is do I end up with the exact same equation as I started with? And here, because we do, we would conclude that we do have this sort of symmetry. Okay, so these are the same as each other, and so we would conclude, yes, I do have x-axis symmetry here. Okay, I want you to notice what happens when we move on to y-axis symmetry. So my original equation was x is equal to y squared minus 3, or did it say plus 3? No, it said minus 3. I'm good. Okay. What I want to do now, since I'm testing for y-axis symmetry, is I want to go ahead and replace all the x's I see with negative x and see if I have any changes. Well, what you'll notice here is that on the left-hand side of this equation, we have negative x in parentheses. Remember, we've talked about in the past when we can just drop those parentheses. We basically said if there's a negative in front of that set of parentheses, then we have to distribute that in. Otherwise, we could just drop them. And so here we just have negative x is equal to y squared minus 3. And the idea is if we try to compare that to what we originally started with, it's not necessarily the same, and we're kind of left without a way to get rid of this extra negative that we introduced by plugging in negative x here. So it does turn out that plugging in negative x is going to matter a lot here. These are not the same. So we'll kind of write that as a conclusion statement. These are not the same. And so what that's going to mean is that we don't have this type of symmetry. So I'm going to say no on this. When you test for origin symmetry, remember that that means you're going to be replacing x and y with negative x and negative y both, respectively, at the same time. So if your original equation was x is equal to y squared minus 3, I'm going to take out x and replace it with negative x. I'm going to take out y and replace it with negative y, and we're going to see what we result in here. So again, this is based on the operations inherent in the equation. And because we've already done the previous two tests, I think we can have a sense of how this is going to work out. Because if I, again, when I square that negative y, I just get positive y squared. But then there's really nothing in here that's going to allow me to get rid of this extra copy of the negative from the left-hand side. So again, this is going to be something where if I try to compare this to what I was originally given, it's not something that's going to be the exact same. And so I would conclude here that we do not have this type of symmetry. So that's going to be a no. All right, I'm going to skip out on making the graphs just for the sake of time in the video, but that's what you're looking out for. These are the algebraic tests to see if you have these types of symmetry. If you plug in negative x or if you plug in negative y, the question is, does it change anything? Do you just get the original equation that you started with back? I believe I did number 3 in class, so I'll end the video here by doing number 5. Okay, so let's take a look at that equation really quickly, right? So we've got this equation. We want to test this for x-axis symmetry, which of course means we're going to take all the y's that we see and replace them with negative y in parentheses, and then see if we get something that is the exact same as what we started with. Okay, well, you'll notice here that on the right-hand side, everything's got an extra copy of a negative in it, so I can go ahead and factor that out if I wanted to, and then you can drop the parentheses on the left-hand side, and then you might notice here that on the left and the right-hand sides, respectively, I've just got these extra copies of negatives, and if I divide both sides by -1, I just end up here with simply y is equal to x squared plus 4. And that is not at all the same thing as what I started with initially. So I would conclude here that I do not have this type of symmetry in this example. Okay, so these are not the same. Not the same. So this is going to be a no. On this next one here, okay, again, starting over the original equation, y is equal to negative x squared, and then it said minus 4. All right. What I would want to do here, again, is take out all the x's that I see and replace them with negative x in parentheses. And so this is a good example of why we would want to go ahead and replace it with negative x in parentheses, because there's a lot happening to your x term here in this equation. And so when we take out x and we replace it with negative x in parentheses, it's going to minimize mistakes, okay? So what's going to end up happening here? Well, right here, if I take negative x and I square it, that's going to end up giving me positive x. And then if I have that extra negative out from in front, that's going to give me negative x squared. And then I still have that minus 4 chilling out back there. So what I realize here is that I do end up with exactly what I started with. These are the exact same as each other. And so I would conclude that I do have this type of symmetry. This is going to be a yes. This does have y-axis symmetry here in this example. So that would be a yes. And then finally, for the test for origin symmetry, I would just want to go ahead and simply test both. So my original was y is equal to negative x squared minus 4. And again, replace all the y's that I see with negative y in parentheses. Replace all the x's that I see with negative x in parentheses. And the rest of this is just going to work out in the exact same way. All right, well, again, because we already did the previous two, we have a sense of how this is going to work out. It looks like, just like in the last example, this negative on the x is going to be resolved by that exponent of 2. But then I have this extra negative on the left-hand side of the equation that I'm left with without a way to get rid of. So what that's going to mean is that I do not have this type of symmetry because these guys are not the exact same. And so this is going to be a no. Okay. There are other examples here in the video, but I will go ahead and do some more of them in the video that's going to come later on for day 2 of section 1.1, so stay tuned for that. But that's all I have for this video. Thank you very much for your attention. As always, if you guys have any questions whatsoever, please feel free to get those answered from me. But that's all I have for this one. Thank you very much for your attention, and I will speak to you in the next one.